So today we are going to do section 7.3. First, let's look at the book. This is the page that's already done. And then, but we mostly just look at this part. And that should be good enough. Next, to page 228 and 229. Let's see, a little closer. Okay, and then on the top and on the bottom. All right. And page 230 and 231. Let's see. All right. No, wait a second here. That's wrinkled. All right, try again. That's page 230. And then a little bit closer on top. And a bit closer on the bottom. Okay. So let's start at page 227. Now with the line integral, the first thing we want to do is exact differentials. What that means is that is it possible to figure out where p dx and q dy is the differential of a certain function big F. In other words, we need it such that if we have a p dx and then a q dy, we need to know in what conditions that we can find big F such that it exists and then f1 is equal to p and f2 equals to q. And how do we find this F? Okay, and so then let's look at the subsection 3.1, the existence of exact differentials. Now first, let's talk about a domain. What is a domain again? A domain is given on page 181, which is, let's see, where's the domain? Right there. A domain is an open connected set by our definition, okay? And so knowing that, so imagine something that's both open and connected. Open means no boundary points, and then connected means not broken up into two pieces. And then let's see, where am I? I lost my page. There it is. Okay, now we are going to have a new definition. A domain is called simply connected if no Jordan curve in D contains in its interior a boundary point of D. Now, what does that mean? So let's imagine there's a D, a set of D, okay, that is open and connected. That's so far so good. Actually, the boundary points are all dotted lines. Maybe I should draw it that way. Yeah, okay. These are dotted lines because it doesn't contain any boundary points. Okay, this thing just got nothing. Yeah, so dotted lines. And then a Jordan curve that's in D. Let's consider some Jordan curve, okay, that contains no Jordan curve in D contains in its interior, that's inside, contains a boundary point. Why would there be a boundary point on the inside of D? The only way that would be possible is if and D being open is that there is a hole in there, okay, and that is D. To be simply connected, D may have no holes. Thank you. So that is that's all that really means. But the technical definition is that no Jordan curve may contain a boundary point. So if that's the case, we'll call simply connected with the star with the star's symbol to mean something is simply connected. So let's look at theorem 4. Theorem 4 says that if we have P and Q, which is C1, okay, in D, and then Q1 equals to P2. Now that resembles the Green's theorem, right? And we're going to be using that in this proof. And then if that is true, then both the necessary and the sufficient condition, those two are necessary and sufficient conditions such that That's, in other words, the if and only if symbol is right there, means the both is both necessary and sufficient that there exists the function f in C2 such that f1 will be p and f2 is going to be q. All right, so next page. To prove, first we prove the direction from top to bottom, okay, the implication. That is first we'll prove that if PQR C1, Q1 is P2, then F exists with those conditions. To prove the existence of F, then the equality of, if once we prove the existence, then F12 equals to F21 because of mixed partials being equal. And that has a name to it, clairvoyant or something, doesn't matter, okay? The point is mixed partials are equal, and then we don't have to, and then we already know that F1 is, and being that Q1 equals P2, then, and F exists, then, and F1 equal to P, F2 equal to Q, then, of course, then Q1, for example, will be F21, right? And then P2 will be F12, and they will be the same. So we only have to prove the existence of F. Now to prove the existence of F, we're going to construct it, okay? We'll define F as the integral from some point inside D to a different point, to the point that we're defining, and of the integral of p dx and q dy, and like this one. Now to define a function like that is, and that's fine, but is this really truly a function? I mean, we can integrate like that, but which path are we taking, and are they the same value? If you define a function that is not path independent, in other words, going the value changes depending on how you get there from the AB to x0, y0, then your function doesn't have a lot of meaning, okay? It's like, what is the function supposed to be? It's not really a function. A function has to be a unique value so that we know, so that it makes sense. Excuse me here. So then, now, first of all, we have to consider that such a line even exists. The line integral, some random line integral exists. Well, it exists because the domain is connected, okay? So it's possible, being that it's connected, the connected definition, let's see, what was the connected definition? Does it say? Open connected. Well, there was, yeah, the connected specifically means that, and right here, back on page 181, the connector point means that any 2 points of D can be joined by a broken line. The word broken means there may be corners. It doesn't mean the line comes in 2 chunks, okay? That's still connected. It just might have a corner. A broken line having a finite number of segments, all of whose points are points of D. All right, so that is why we're able to draw this line from AB to X to XY. So that the segments, such a line exists by the definition of a domain. That's what we just read. Now, the next sentence is important, okay? It is easy to see that the segment of this broken line may be taken parallel to the axis. Is it easy? Let's just say it is right now, okay? The book says it's easy, so we'll accept it. And the actual proof of this kind of thing is taught and more in, I think, I don't remember, topology or something. But anyway, so yeah, topology proves a lot of stuff that's easy to see. All right, so we just assume that we can see that if we can get from point A to point B on some path, we can do it in such a way that the road is built only on the east-west and north-south directions only. Okay, you just keep doing that and adjusting the path, and it should be able to get from the first point to the second point without going diagonal or something. You know, there should be always a way to do this kind of path. All right, and it's easy to see, so you should be able to see it. The book says so. Now, so we have a path, and why are we choosing this kind of path? Because what happens is when you choose this kind of path, then you will be enclosing some kind of a pack of rectangles. Here, let's look at the illustration of this. Okay, so here's from AB, we have two different paths. That's x, 0, y, 0. Okay, the paths go up, down, and so on. But eventually, the two paths will eventually end up enclosing a bunch of rectangles. Yeah. So then the rectangles might even collapse, okay, so that they're just one line, but that doesn't affect our proof. Our proof works the same way, whether the rectangle actually is a true rectangle or maybe is collapsed into just a line. Either way, so then our two paths will enclose a bunch of rectangles. Oh, actually, yeah, they did show that this rectangle right here collapsed. See, it's just a line, which is okay. Our argument holds. So is enclose a bunch of rectangles, and then now the next thing we're going to prove is that the function f is defined this way, is a single valued function that does not depend upon path. Now remember, f is defined. Now give me a second here. I thought of something. So the big F that we defined so far is a function that goes from point A, integrates from the first point AB to the second point XY through a path that's only goes north south. Okay, that's our definition. But it doesn't matter how, just as long as it does it that way. Okay, and well. Anyway, so that's that. Now, if the function f is defined that way, then it is a single valued function. That is, the integral, it does not depend on which path you take, as long as the path is rectangular. Now, how do we, the book calls it a single valued function. Well, in basic math, then all functions are single valued. But nowadays, we loosen the requirement a little bit. So we specify that f is a single valued function. That is, it's not going to come out with some other number. Okay? It's the function f is just like we learned it, that it has a defined result, that you're not stuck with a bunch of answers, you don't know which one to pick. So then to consider now to show that this is single valued, which it just means it doesn't matter which path you take, the integral will end up with the same answer. Then let's consider two such lines that are parallel, the two such broken lines in D star with segments parallel to the axis and joining AB to XY, which is what we have seen. Okay, imagine these are two lines. They're different, but they both got there. You know, if that's the case, they will form the boundaries of a finite number of rectangles in which, okay, that is. So we define f, and then in this so we have a bunch of rectangles, and all the rectangles are such that Q1 equal to P2 because that's given. Okay, right now we're proving the existence. Now let's see. No, we're not. Sorry, Q1 is equal to P2 is given, okay? Because right now, try to remember what I'm doing. We're proving the forward direction. That is, we're given Q1 and P2 are equal, and we're proving that PF exists. So, okay. So then, being that Q1 equal to P2 is given, then it applies on all these little rectangles that we've worked on, and so far. So then we can apply Green's theorem. Then by Green's theorem, being that Q1 equals to P2, and each rectangle is an Rx and Ry. Now we're looking at the first Green's theorem, which is theorem 2 on page 223, which says that if the region R is Rx and Ry, then and P and Q is in C1, then Green's theorem applies. Okay, then now in this part, this is where that no hole trick comes in, because if there is all these rectangles must be Rx and Ry. Now they are Rx and Ry because they're rectangles, but more importantly, they are. This is a region without a hole in it, because if your rectangle has a hole in it, if any of these rectangles encloses a hole, then the region is no longer Rx or Ry, because a rectangle with a hole is no longer Rx. You got to cut it up if possible or something like that, right? So this is where, but being that there's no hole, everything's legit and everything's working out, and so it is, each rectangle is guaranteed to be both Rx and Ry. So by Green's theorem, then the line integral is around it is going to be Q1 minus P2, and being that Q1 minus P2, this integral has to be 0. Okay, then so the integral is around each rectangle is 0. So then that means you sum it all up. There are a finite number of rectangles. Summing it all up means the original rectangle going all the way up there and then going back through those two paths that we picked. And so then the entire line integral 1, which is the one on top, okay, then this line integral has to be equal to 0. And that proves that the integral 1 is independent of path. And okay, now that is independent, that is, the function f is well defined. If it doesn't matter how you get, the function f is defined such that it doesn't matter how you get there, okay, from ab to x0, y0, you will always come up with the same answer. All right. Well, that's because if you go around it is 0, that means going to that point the value is the same. Maybe I should say that. Let me write that out. Because as we've been doing, if we have, say, integrating from this point to this point, going through gamma 1, and then you go back, and going gamma 2 is backwards, so there's a minus sign. If the gamma 1 minus gamma 2 is equal to 0, that would mean that these two integrals are the same. And so next, so it's independent of path, and what does that tell us? Now, if that is the case, we're still trying to prove the existence. Now, let me think. Actually, by proving that it's independent of path, we have proven the existence. Okay, so the first half of the theorem is done. Now, second half is we need to prove proving backwards. That is, if there exists f such that f1 is p and f2 is q, then the q1 equals a p2 and stuff. And we're going to prove it by actually doing the calculations. Now, this let's consider the point x0, y0, okay, which I draw right here. Now, this point is in the center of some small circle K, which lies entirely inside the domain D. That's because the domain D is open. If it's open, every point of the domain contains a small circle in which is completely contained within the domain. That's the definition of openness. Now, we will choose some small delta x such that this, if we move it over in the x direction just a little bit, this point is still in the small circle K, which means it's still inside domain. Okay, so everything's good. That point is still the interior point of the domain D. And once we do that, we pull this the same trick that we've done before. This looks familiar, but so then we calculate delta f delta x. Now delta f delta x, then we write it out by its definition would be just what was f again? F is up there. Okay, then we just write it out. That would be equal to delta x and the integral of the difference. That is we're integrating from here to there. This is x0 plus delta x, and y holds the same. Okay, so it's a perfectly horizontal line. Now once this integral, to calculate what is this, on this integral being that it's a perfectly horizontal line and there is no change in y, so dy equals to 0. Okay, it doesn't ever move. So if dy equals to 0, then this whole thing is then the q dy part is 0. And so then we have the next thing we're going to do is apply it only equals to the pdx part. So we will let's see. Right, we're going to yank the p out of the integration by the law of the mean. Okay, as you can see, the law of the mean is extremely useful. So here's the integral, right? And we'll just pull it out. And if we pull it out, then if we pull out p, then it will be multiplied by the difference is that minus the top limit minus the bottom limit, which is just delta x. And then so it's equals to p delta x, which the delta x is canceled out with the one down here. So we only have the p left, and this point is somewhere between somewhere in here to apply the mean value theorem. Okay, so for x0 plus theta delta x, that means a point in between. Then we can yank it out and apply the MVT. And once we do that, then we let delta x goes to 0. Then we have just proven that f1 equals to p. And in an nearly identical argument, we will also prove that f2 equals to q, and that concludes the proof of theorem 4. So to recap theorem 4, to find such an f, okay, where we have pq and such that q1 equals to p2, then we can find some kind of a function that where f1 equals to p and f2 equals to q, but only if q1 equals to p2, is that we can find such a function. And the function works out nicely as some kind of the differential is exactly p dx and q dy. Next, let's look at page 229. Suppose we have a differential equation in the form of p dx plus q dy equal to 0. Now, by the previous proof, we can then figure out that and also the requirement that q1 equals to p2. Then with that, we have from the previous theorem that there exists a big F, okay, where big F is constant, and it is the antiderivative or the primitive of the differential equation. Now the question is, and where satisfies the requirements of the where big F is by theorem 4 is where f1 equals to p and f2 equals to q. So then the question is, so our big F, however, is defined only along rectangular lines or polygon lines, right? So what if we want it to be not rectangular but any old line? Okay, just so that the path does not have to be polygonal lines. So then, so in the next theorem, we're going to show that the value of the integral does not matter if by the change of path. Doesn't matter what path you use. So then let's look at theorem 5, which is which says that p and q are c1, okay, and then q1 equals to p2. Now then gamma is a regular curve. Just in other words, gamma is any old curve, not those perfectly rectangular things. then in that case, the integral is still independent of gamma. It doesn't matter how you get there, you still get the same value, whether gamma is rectangular or not. So the proof is this. We have, of course, being that gamma is some regular curve, we can parameterize it with phi t and psi t, and then with so we are going to define by theorem 4, we're going to the integral of p dx plus q dy is equal to the function f with phi and psi plugged in. So once we plug it in, we have, of course, something like this. Okay, this is based on the definition over here. We're just we're going to replace x is phi of t, y is psi of t in the definition right here. Now, if we did that, then the integration would go from t will go from 0 to 1. And what is the whole thing inside? That happens to be exactly the d by dt of f, okay, with phi and psi inside. And as a result, then, and this thing, we know how to integrate it. This thing, to integrate from 0 to 1 of this thing is the same, exactly f of the endpoint minus f of the initial point. And that equals to the integral that we're looking for. Okay, and notice that this answer here does not matter. It totally, the phi and psi disappeared. That is, it doesn't matter which phi and psi we use, and it will come out with the same answer. The answer being the endpoint, the value of f at the endpoint minus the value of f at the initial point, and therefore we have proven that this is the integral is independent of path. So since the result doesn't even depend on phi or psi. Now notice that this reminds you of the fundamental theorem of calculus, right? Which says that the where the definite integral is, we use the indefinite integral to calculate, and by doing this endpoint subtraction trick. So then, if we can, as a result, we have a quick way of calculating in the integral 1. Now please look at the example A. We have where we redo the example C on page 220. So please do this yourself, okay? This is a demonstration of what we just did. So and it's very straightforward. So you have to figure out some kind of an antiderivative. So that's example A, and then we'll move on to the next page. So next, let's look at page 230, theorem 6, which reads, if P and Q are in C1, okay, so P and Q are in C1, now we understand that. Then, if Q1 equals to Q2 in the whole domain, then the PDX, the integral of PDX plus the QDY will be 0 for every regular closed curve. Well, it's closed for one thing, and then the backwards is also true. That's the if and only if condition. Whereas if the integral of PDX and QDY is 0 for every closed curve, then Q1 will be equal to P2 in the entire D star. Now to prove this, let's prove the forward implication, which is the result of theorem 5. What was theorem 5 on the previous page again? That is, if we have Q1 equals to P2 and gamma is any regular curve, then the integral path is independent. Then then that means if we go all the way, if the gamma is a closed curve, then we came all the way to the end. So the value of the integral would be just the big F AB minus itself, okay, which is going to be 0. Because then now we can just pretend that the endpoint and initial point are the same point. So then the forward implication is basically a restating of theorem 5. Now what about the backwards integration? That is, assuming that integral of PDX and QDY is 0 for every curve gamma, then how do we prove that Q1 equals to P2? Now, to prove the opposite implication, let's assume that Q1 minus P2 is bigger than 0 at some point, at x0, y0, right here, my same point. Now, if that is the case, then there exists a circle K such that where there's a neighborhood, in other words, where Q1 minus P2 has to be bigger than 0 in the entire tiny neighborhood. That's because, remember, P1 and remember, P and Q are C1. That means they're the first partial derivatives don't just exist, but also continuous. Now, knowing that if it's bigger than 0 in an entire little circle domain, that means we can apply Green's theorem, which gives us the Q1 minus P2 integrating is gonna be Q1 minus P2 is bigger than 0 in the entire neighborhood. So when we do the integration, this the integrand in here is bigger than 0 the whole time, which means when by Green's theorem, this equals to that, and that had better be bigger than 0 too. But we are assuming that we're already given that it equals to 0. Okay, we're proving backwards. So we know that this is equal to 0, so the fact that it's bigger than 0 is not acceptable. There is a contradiction. Now, that's assuming it's bigger than 0. Assuming it's less than 0 works exactly the same way. It will also obtain a contradiction, which means they better be the same, and the proof is complete. And notice that in this particular proof, gamma can even cross itself. Now, normally a regular curve that is not allowed to cross itself. Okay, it has the definition of a regular curve on a previous page right here is that a curve is regular if it has no double points. That means it doesn't repeat, it doesn't cross itself or even touch itself again. If the interval and so on. But in this theorem, in this theorem, even though we do require gamma to be a regular curve, it is okay. But the theorem still works even if gamma crosses itself sometimes. Then probably only if a finite number of times. Okay, then but anyway, so that's that. So next, let's consider section 3.4. Which is there's an example of a counterexample of a case of where integrating something that is not whose domain D is not simply connected. It's got a hole at the origin. Now, if that is the case, all the theorems we have are not going to work out. Because if you calculate the integral, which please do that yourself, okay? I've done it right here. We just, you crank out PDX and QDY and substitute, and very soon you realize that going around the unit circle of this thing, being there is a hole at the origin, the unit circle contains the hole, then we have the integral is going to end up being 2 pi. Well, whatever it is, it isn't 0, okay? Anyway, so please do that yourself, and notice the certain comments. The region then is considered multiply connected. So simple. So things with holes in it are called multiply connected. Okay, but we can still apply the theorems we have learned in this section to multiply connected regions by cutting the domain into pieces. Okay, so that it becomes cut it across the whole somehow. So that so in each chunk of the domain that got cut, the remaining pieces, the theorems will apply as long as the remaining pieces have no holes in it. So that is So please do that yourself. I assume I got that correct, but I hope I didn't make any mistakes there. But I think the integration is fairly straightforward, so it should be okay. And so that we have come to the end of this section. For homework, please do, let's see, the homework is right here, 230, right? Yes, page 230 for homework. Please do problems 1, 2, 3, 4, 5, 6, 8, 9, 10, and 12, 13, and 14. And I will talk about the homework in the next video.